Hello viewers, this is Jeyapradha, Assistant Professor, SFR College. Today I am going to discuss about B tree in data structures. Before going to the topic, let's see the objectives of B tree. First of all, we understand the basic concepts, needs and operations of B tree. Then we analyze the properties of B tree, demonstrate the working of various operations. Finally, we have assessed the applications and advantages of B tree. Let's see one by one. First one. What is B tree? B tree, the name itself, it's a balancing tree. It's a self-balancing tree data structure that maintains stored data and allows insertion, deletion and searching operations. It is commonly used in databases and file system. The file system which have large amount of data, it needs to be efficiently stored and retrieved, especially when data is stored in external memory. Assume that B tree is a M-way tree. It have M children and M-1 key of order M. So what about the structure of a B tree? B tree have root, nodes and children. The root is the topmost node, which can either be a leaf or internal node. Node means it have keys and pointers to child nodes. Children have an internal node contain child pointers that points to other nodes. So next one is, what is the need or purpose of B tree? The need for B tree emerged as the demand for faster access to physical storage media like hard disk, backup storage devices like that. So there were a demand for data structure that reduced the number of disk accesses. On the other hand, we have many data structures like binary tree, AVL tree, but these are all have to store a significant number of keys, and the height of such a tree have growing fast. The time it takes to access them are increasing. So this can be resolved by using B tree because it can store multiple keys inside a single node and has several child nodes. It considerably reduces the height and increases the disk access speed also. Here is the example for B tree. Next we see the most important or important characteristics of B tree. So first one is balanced. All leaf nodes are at the same depth, ensuring the tree remains balanced. This leads to solve time complexity for search, insert and delete operations. The next important feature is multi-way tree. Each node can have more than two children, especially it have an order of M and have M-1 keys and M children in each node. Third one is sorted keys. The keys within each node are kept sorted, which also leads binary search within each node. Fourth one is node contain multiple keys. Each internal node contains a number of keys, so that divide the range of keys into different sub-ranges. So last one, efficient disk storage. B trees are designed to minimize disk operations, and it is suitable for storage systems that have large amount of data. As a single node can store multiple keys and child pointers, this reduces the disk access time also. So next one is properties of B tree. There are several properties. They are all leaf nodes of a B tree are at the same level, that is they have the same depth and height of the tree. Second one, the key of each node of a B tree. In case of multiple keys, it should be stored in an ascending order. Third one, in a B tree, all leaf node except root node should have M/2 children. All nodes except root node should have M/2 minus 1 keys. If a root node is a leaf node, then it will have no children and will have at least 1 key. But if the root node is a non-leaf node, then it will have at least 2 children and at least 1 key. A non-leaf node with n-1 key value should have non-null children. So these are the main properties associated with the B tree. So next, see the operations of B tree one by one. First one is search operation. The search operation starts from the root and travels down the tree, comparing keys at each node to find the desired key. So here the procedure, let the key to be searched is key. Start from the root and recursively traverse down. Second step, for every visitor non-leaf node, it can be noted the current node contains k, return that node, or else it determine the appropriate children to traverse. This is the child just before the key greater than k. So last step, if we reach a leaf node and don't find k in the leaf node, then return null. So consider the given example. Let's look for item 49 in the B tree given. The procedure is compare item 49 to node 78, which is the root node. Move to the left subtree since 49 is less than 78. So second, since 40 is less than 49, but 56 comparing to 56 it is less than 56, but comparing to 40 it is greater than 40. Move to the right subtree of 40. If 49 is greater than 45, so move to the right and then compare the 49 with the node. Match is found, then return the value. So the height of the tree affects the search in a B tree. To search an element in a B tree, the search technique remains of log n time needs. So next we go to insert operation of B tree. Insertion is done by finding the appropriate leaf node and placing the key in sorted order. At the leaf node level, insertions are made. In order to place an item into B tree, the algorithm should be as followed. Navigate the B tree until you find the suitable leaf node to insert a node. If there are fewer than m-1 key in the leaf node, insert the elements in the ascending order. Otherwise, if the leaf node comprises m-1 key, proceeds to the next step, that is, in the rising sequence of elements, add the new element. In the middle, divide the node into two nodes. In the median element, it should be pushed up to the parent node. If the parent node has m-1 number of keys as the child node, split it as well as using the previous steps. Let's see the example. As indicated in the diagram, in the B tree of order 5, insert node in step 1. Because 8 will be put to the right of 5, so enter 8. There are now 5 keys in the node, which is more than given keys. So as a result, divide the node from the median, which is number 8, and push it up to the parent node illustrated in steps 2 and steps 3. So next operation is a deletion operation. So deletion operation involves removing a key and then rebalancing the tree, if necessary by merging or redistributing the key between nodes. So determine the location of the leaf node, first step. Second one, if the leaf node has more than m/2 keys, delete the required key from the node. Third step, if the leaf node lacks m/2 keys, fill in the gaps with the element from the right or left sibling. So in this case, we note that if the left sibling has more than m/2 elements, means shift the intervening element downwards to the node where the key is deleted and push the larger element back to its parent. Or if the right sibling has more than m/2 items, shift the intervening element downwards to the node where that key is deleted and push the smaller element up to the parent level. Fourth step, create a new leaf node by merging two leaf nodes and the parent nodes element if neither sibling has more than m/2 elements. Last step, if the parent has less than m/2 nodes, repeat the operations as well as if the node to be destroyed in an internal node, it's in order successor or predecessor should be inserted. The process will be as the same. The node is deleted from the leaf node because the successor would always be on the leaf node. Let's see the example. As indicated in the diagram, remove node 53 from B tree of the order 5. Element 49's right child contains the number 53. Remove it in step 2. Now that 57 is the only element left in the node, the minimum number of element required in B tree of rank 5 is 2. Because the element in its left and right subtrees are similar, insufficient, so combine it with the left sibling of the intervening element of the parent, that is 49 in the node at last in the step. So finally we have removed the node 53 from the tree. So last one, and we have discussed about the applications and advantages of B-tree. So B-tree have used in large databases to access data stored on the disk, or used in CAD systems to organize and search for geometric data, or used in natural language processing, networks, cryptography, in all fields. So advantages are notable self-balancing, high concurrency and high throughput, efficient storage and utilization. So at conclude, B-tree are a smart and efficient way to handle large amount of data. Their balanced structure and ability to store multiple keys in one node make searching, adding and deleting data fast and reliable. So B-tree are especially used for systems like databases, file storage, where quick access to data is important. Thank you, viewers.